Okay, can everybody hear me out there? I guess hard to tell. Let me go ahead and begin and we'll get started. My name is Joel Brock. I'm a professor at Cornell University in the School of Applied and Engineering Physics and the director of the Cornell High Energy Synchrotron Source. And today is the first of a 4-lecture series on Introduction to X-rays, their interaction with matter, scattering, spectroscopy, and so on. And it aimed at students who are roughly senior year or first year graduate students, and it doesn't assume that you have any previous experience with synchrotrons or X-ray work. So it's basically meant to be an introduction to everybody. So let me go forward. Let's see.
Okay, we are like 10 minutes from 9, so let's start. Joel, thank you everybody for being here on this beginning of a section of courses that we plan for you to get more information on the subjects that we have in our project, and with X-ray and spectroscopy and electrochemistry. It's going to be 3 weeks of courses, all at 9 a.m. We will be really happy to have you here, so you can have all the deeps inside about the information that we need to interpret our data and understand what we get from our experiments. This section is going to be recorded, so if anyone doesn't want to be in the recording, because the chat is also recorded, this is the moment to, you can excuse yourself if you don't want to be part of the recording. If you want to be in the class but you don't want to be part of the recording, take notes and then make the questions. So we're going to start recording at this moment. I'm going to be...
Maria, I had already just started. So...
Oh, you started? Okay, sorry. Okay, thank you. So let's go, Joel. Go with you.
Good. So welcome everybody. I'll start, repeat just a little bit. My name is Joel Brock. I'm from Cornell University School of Applied and Engineering Physics and director of the synchrotron. And this is, in my part, it's the first of a 4-lecture series. And it's also the first series. Next week, Professor Brunia will be speaking about electrochemistry, and the following week, I think Professor Cabrera will be speaking. So it's actually very exciting to have all of these courses. Looking forward to it. So to begin, before we talk about X-rays, we need to sort of examine what an X-ray is. And for the purposes of the next 4 weeks, and generically true, you should think of X-rays as light. Right, and that I've got the full electromagnetic spectrum out here in front of you, going all the way from radio waves, which are many meters long, and large things, all the way through visible light, which is about the size of bacteria or something, and into the ultraviolet and the X-ray, out to the gamma rays. And so the key thing to remember is an X-ray is about 10⁻⁻10 meters, that's 1 angstrom, and the characteristic size of an atom. And so the visible spectrum in contrast is over here, and it's about 0.5 micron in size. But all of these are just different wavelengths of electromagnetic radiation, and that because of their wavelength, they're sensitive to different length scales, they have different energies and so on. But the physics is all the same for electromagnetic radiation. And so, just repeating briefly, for purposes of this course, there's no really rigorous definition, but I'm going to assume for our case that X-rays have a wavelength of about 1 angstrom. Some people will tell you that several nanometers in X-ray, or that hundreds are, although Okay, my battery on my laptop may crap out. I'm sorry that my charging circuit doesn't work. So if I disappear, I'll come back in a few minutes. This been a problem. It's plugged in, but we'll see if it. So I'm getting warning messages. Okay. So the key thing about being part of electromagnetic radiation is that both the electric and magnetic fields obey the wave equation. And I've written it down below for the case of the electric field. And on the left-hand side is the Laplacian applied to electric field, and equal to the second time derivative of the electric field with the speed of light here down in the denominator. We know a lot about this partial differential equation. In particular, that the most general solution to it is the sum of two shapes. You have one moving to the left and one moving to the right at some speed v. So whatever the shape is, you can have either moving to the left or the right. So any function, e here, that has this argument will satisfy the wave equation. All you have to do to show that to yourself is plug this equation back into the wave equation, and you'll see that it's true. Where here I'm using v and c interchangeably. There's a specific solution choice here, or due to Fourier theory, we can make this version of the electric field equal to a sine wave or a cosine wave, either one. So if we go to one dimension, then you can write the electric field is just a sine wave, which is moving one direction or the other. And it's shown schematically down here below, where our first plot the electric field is a function of position at a particular time, or is a function of time at a particular position. And they have very similar shapes, you can see below. That's a very useful way to get started. Similarly, for Fourier theory, I'm just going to quote some results at you. If you're not familiar with this, just look at the pictures below. But if I have a function, which is a variable c, in our case, remember this was the argument to my shape function, I can write it as a sum of over different wave numbers k. With a Fourier transform part. The Fourier transform, I go back and forth between these two representations through this transformation process. And this is particularly useful. So for example, if I want to have a traveling wave packet, I'll show this thing down here. It has, here's my traveling wave that we've been talking about, and I put a Gaussian on it, and you get this nice shape, and it just propagates back and forth. Am I back, Lamari?
Yes, but not the presentation, just your video.
Yeah. Oh, not the presentation? Okay. Sorry, my computer just crashed and rebooted. Let's see. Probably have to.
Now we can see your presentation. It's still in the, oh, there you go.
Okay, and where was I when we crashed?
Go back. I think one more. No, that's the next one. There.
Okay. What's this thing doing? Let me stop my personal video so that you won't be able to see me anymore, but that may help my power here. Let's see, how's this doing? Gonna have to buy a new computer very soon. Let's try this again. Very sorry, everybody. So can you still see me and hear me, Lamari?
I can still see the presentation and hear you, yes.
Okay, good. Okay, I don't have any feedback at all on you guys right now. Okay, so the solutions to the wave equation, I'll start back up here again. And my pointer turned back on. And the most general solution to the wave equation is the sum of two shapes, one moving to the left and one moving to the right. Right, so that if you think about a shape of any variable here, or if I make that argument to that variable, so the distance minus things, this is a shape moving to the right, and this is a shape moving to the left. And these are any arbitrary function that will satisfy the wave equation. You can verify that for yourself just by plugging it into the slide, into the wave equation here. If you plug this solution into that, it just works. Or a specific example of this are the sine waves and cosine lines with this particular function. They're very useful because of Fourier theory, where I can take a sum of those sine waves and make any shape I want. And this is the integral version of it, going back and forth, where I can go from C to K, back and forth here, and see the an example of why this is useful is I can represent a traveling wave packet. So, for example, this is a plane wave moving through, and you see all the little oscillations here, and it's multiplied by a Gaussian, which you see is in the amplitude here. So the amplitude is moving, and this thing just moves through space. This is what a wave packet looks like. Right, so this is one representation, or I can look at it as a sum of plane waves where I add up all these different k values. And again, there's a Gaussian, but in k space now. And so I have my choice. I can work in real space or reciprocal space going back and forth, whichever is more convenient for me. And so that becomes a very useful from computational standpoint to go back and forth. But it allows us to do several things. We know from the Heisenberg uncertainty principle or from the wave equation, either one, that there's an uncertainty in time and frequency due to the transform relationship. That means anytime I have a pulse that has a finite duration, and it will have a finite spread of frequencies included. And so just give a couple examples. I'll say that if I think about the K alpha radiation from a copper X-ray tube, it has the line width, the natural line width of that tube is about 1 electron volt wide. That means H bar times delta omega is about 1 electron volt. If you just calculate what is delta T, you find out it's about half a femtosecond. And so you're like, well, that's pretty wild, but if at 10 kilovolts, if you ask how many oscillations are in a femtosecond, 10 kilovolts corresponds to about 10 to the 21 hertz. That means there's about 1 million oscillations in the pulse. Also, although we have very short pulses on the scale of a femtosecond coming out of your tube, there are about 1 million oscillations. So when we're doing our calculations, we can treat it as a steady state source, but we have to be, recognize that we're really dealing with pulses coming back and forth. At the synchrotron, this bandwidth may be different. It might be a fraction of an electron volt, or it might be several electron volts. But the same idea we can calculate based on this idea what is the, for any finite pulse length, what is the energy spread? Now, because X-rays are electromagnetic waves, Maxwell's equations puts additional constraints on the solution. So here I've plotted in blue the electric field we were just talking about, through this relationship here in Maxwell's equations, if I take a derivative of the blue line and this cross product flips it around, that what we see is the magnetic field then, and is orthogonal to the red is meant to show you the magnetic field. It points in a direction orthogonal to the electric field. And both of the fields have to be perpendicular to the direction of propagation. And so you get this kind of picture sketched up above where the electric and magnetic fields are out of phase, perpendicular to each other, and perpendicular to the direction of propagation. And this is just generically true for electromagnetic fields, and specifically true for X-rays. So everything I've shown you so far is classical, but we frequently slip into jargon and talk about photons. And so what is a photon? And basic idea is you think of a wave packet, such as the one sketched below, that both the energy and the momentum are localized inside that wave packet. So as the wave packet moves, it carries energy and momentum with it, and it's moving at the speed of light. Again, from standard theory, we can calculate the energy density, and it goes like the square of the electric field and the square of the magnetic field. And if you think about these two being out of phase, it's like this is like sine squared plus cosine squared. The energy density is actually a constant. It doesn't oscillate. It just moves back and forth. Okay. So in quantum mechanics, then we put some limits on classical mechanics. I said that the energy and momentum move with it. Turns out that the amount of energy and momentum in a wave packet is quantized. And it's very, very small, these quantities, so we normally don't see it, but it is quantized. And in essence, then the intensity of the X-ray beam is proportional to the number of photons passing through a plane per unit time. And so we can get a little, and what you should think of is the smallest possible wave packet that can be traveling along is a single photon. So the numerical relation between energy, wavelength, and photon energy is given by this expression here, where the wavelength is some fundamental constants, the Planck's constant, speed of light, divided by the energy of the photon. This is h bar omega down here is the way to think about that, and comes from if you set lambda nu equal to c, and then you divide through by the energy, you can derive this formula. But so the wavelength and the energy have a reciprocal relationship. And in the units of kilovolts and angstroms, that number is about 12.4. Okay, so how do we get quantized radiation? What are the rules? Well, and classically, the wavelength of light is quantized by localization. And you're all really familiar with this. I know a lot of you play instruments and violins, pianos, flutes, tubas, trombones, whatever. And we can get a single tone or a single wavelength by setting the length and the tension of a string. And the simplest way to think about it, or it could be in a brass instrument, an acoustic cavity. That's the basic idea. And that, the way we tune something is by changing the length of the string or changing the tension. You tune a brass instrument or a flute by changing the volume. That's a completely classical idea. So we can set the wavelength precisely this way. What quantum mechanics does is something which is very counterintuitive, and it tells you that the amplitude of that wave is what's quantized. So it's not that the frequency is quantized, but the amplitude of the wave is quantized. And that's a very bizarre concept to get control of or get your head through. Okay, so then now we've got an idea of what an X-ray is. So how do X-rays interact with matter? And it turns out there's just two ways they can do this. They can scatter or they can be absorbed. And So let's go through these. So if the medium is dense, so it's a solid and not a gas, so on, but it can be really convenient, as in your physics courses, to treat the materials as being a continuous thing and that has a surface. So on one side of the universe is a vacuum, on the other side is your material. And this very simple approximation leads us to the familiar concepts of reflection and refraction, which you're familiar with. So we've all seen the concept of a mirror or light reflecting off of a window, whatever it is. Refraction is also used in visible light for lenses and so on. So those are the two concepts, and they basically are introduced by introducing this interface. In addition, there's the concept of scattering. And scattering is actually the dominant interaction of light with materials. So let's go through this one a little bit more carefully. Okay, the scattering, well, first let's consider the scattering of electromagnetic wave by a single point charge of magnitude q. So I've got this little tiny point charge sitting in space. The electromagnetic wave has an electric field, and that electric field exerts a force on a charge, and this is very simple. The force is proportional to the charge times and the electric field. And using Newton's second law, this force accelerates the point charge. So F is equal to ma. So the acceleration is going to, mass times acceleration is going to be equal to q times e. The only other thing we need to remember that anytime you accelerate a charge, it radiates an electric field. And it's that radiated field that's the scattered wave. So one wave comes in, shakes the charge, or as it shakes the charge, that creates an acceleration of the charge. That acceleration radiates a new electromagnetic field. So the second way that an X-ray can interact with matter is to be the photoelectric effect. And this requires an atom. And so the atom can actually absorb a photon and then change its energy state. Okay. So for the rest of the course, we're basically going to talk only about scattering and absorption. So those are the two mechanisms that are possible to interact with light. Okay, let's go back to scattering. And what I said in words, we're going to go through a little bit more detail now. Consider in detail this interaction of electromagnetic plane wave with a single point charge. And so here, the electromagnetic plane wave, this is my, I'm assuming the electric field looks like sine and kx minus ct. Okay, and I'm showing it propagating to the right here. It has a wave number k moving in this direction, and these are the lines of constant phase coming by. This thing is coming by, and I'm assuming there's an atom here, or a point charge here, and as this wave hits it, this point charge feels a force F. That F can be decomposed into mass times the acceleration, so this point charge has a mass m, and it will be accelerated here. For non-relativistic motion of this point charge, there's a very simple formula that describes the radiation field. And this stuff out in front here is just units. Don't worry about this. This is the size of the charge, which is oscillating. That makes sense. There's a fundamental constant here, the speed of light. What it tells me is that the radiated field looks like the acceleration divided by the distance from the charge to my detector. So if I'm looking out here in space at the detector, which is located at some position r, my point charge, which I assume here is at the origin, and that the field falls off like 1 over the radius, and it's just proportional to the acceleration. Now there's a couple little caveats in here. The first one is that it takes a little while for this wave to propagate from the accelerating charge in my detector. And so when I'm out here looking at the radiated field, the wave which gets to me has actually been traveling for a while. So I see the acceleration as it was. I take this distance r divided by c, that's the difference in time. I need to go backwards in time a little bit. So what I'm seeing back here is the way the acceleration was some time ago. also there's a perpendicular marker here. What that tells me is that as I look back down at the source, I only see the parts of the acceleration which are perpendicular to my line of sight. I can't see motions which are coming along the radius vector here. So I just see the perpendicular component of the acceleration and at the retarded time t, because I'm basically looking into the past. So if I take that previous expression, on this expression for the radiated field, plug everything back in together, I can calculate my acceleration from my the original thing. This is my initial field, which has come in. That since x is 0 for the location of the charge, the kx part has dropped out, and I just then substitute this thing into my previous expression for the perpendicular component of the electric field, and I come up with a very simple formula here. So this is units. It's different if I'm using SI units or CGS units and so on, so let's not worry about that for the time being. This was the dynamical components that came from Newton's second law and from the Lorentz force law. This is just straightforward stuff, and the radiation law. And so I've now come up with something which is very simple. The radiation field, this is the radiated field sitting way out here. It's proportional to the amplitude of the incoming field, and this is a unit vector pointing perpendicular here. It falls off like R, but it's a plane wave moving out. So I've got this thing here just shooting out, it's a circular thing shooting out this direction. This is just a circular wave, or a spherical wave propagating outward with an amplitude given by the incident beam. And so everything here is on the radiation field is completely controlled by my incident electric or incident wave and the properties of the point charge. Okay, now we've got to be a little bit more cautious because I rarely care about the response of one single point charge. If the world wouldn't be a very interesting place if all we had was isolated point charge, single electron. And so what I want to do is expand this formula, which was for a single point charge, to a formula where I have lots of point charges here. So I'm going to have some region of space which has a distributed density. And so rather than having a Q, I'm going to have a little volume element times a charge density, or density, and this is my little delta Q. And each one of these has to live at some position R prime. So where before I had just a simple distance R, I now have to have the distance from my detector out here at R minus wherever the point charge is. So if I set R prime equal to 0, you'll see this is just the previous expression. And then I have to add up all these little volume elements or wherever my charges are. And I also have to be a little more careful about my retarded time, which before didn't have a position dependence, but I have, because different parts of the sample will be having different phase factors in this moving through, I have to keep all of this stuff together. But if I put everything together, I come up with this very simple formula here. Or this stuff is all the same, and now I have a part here. Okay, but we can simplify this thing. And a little bit of algebra here that you can either follow through the algebra or just trust me at the end. But the basic idea is we're going to make an approximation. So far, everything, there are no approximations other than the don't have a relativistic point charge. So if I take in the denominator, I had a bunch of terms that look like this distance, and of course that's just a vector difference, and so magnitude of this vector is given by this simple expression here. You just multiply it out. But we're going to make the approximation that the distance to the detector R is much larger than the size of my sample. If that's true, I can use R prime over R as an expansion parameter. So if I just pull the R out front, this is exact to this point. But if I neglect this piece here, relative to this piece, so neglect the quadratic term to the linear one, I can just expand my square root, and I get a very simple expression now. And so if I just replace all of my pieces here, this thing here with this expression here, come up with this expression here, all right, just substituting in, I can then pull out the parts which depend on R and T, and I get my original plane wave back, plus this new piece over here that looks like Ki dot R. This is just a phase factor, which tells me how the wave is interacting with the incident wave is interacting. And then this piece, which tells me the phase of the exit wave. Okay? If I define a new wave vector, K final, which is just omega over C times R hat, I can simplify this whole expression into this here. So I move all this stuff back out front, which we recognized from before. That's my spherical wave going out. Where before I just had a Q sitting here, I now have little Q's, but each little volume element is added up with a new phase factor. And the phase factor is given by the vector difference between the incoming K and the outgoing K. And this is the scattering vector Q that you're familiar with. So my radiated field out here, in the end, depends on, this is basically a charge term here. This is the oscillating charge with a little bit of phase factors as all these waves move through here. Right. Okay, let's go to measurable stuff. But this is all pretty esoteric so far, so I actually want to do an experiment. And so the first thing to do is I'm going to divide out my incident field because I almost never do absolute measurements. So let me take the ratios, and this slides everything to one side. So this is now a unitless number, right? It's an electric field divided by an electric field. And it simplifies things a little bit. The other thing, I'm going to, I can replace all of this stuff here. It turns out this is the classical radius of the electron, or the Thomson scattering length. It's given here. There are the, if you calculate the energy, the potential energy of the Coulomb effect of an electron and of a uniform density and set that equal to mc squared, there you'll get this expression here. That's one way, it's called the classical radius of the electron, but it's roughly the size of an electron, so you can think of it. Or that it's also the Thomson scattering length. It's a very small distance. And then I can define this thing, which is basically a Fourier transform, that I'm taking the charge density in real space and Fourier transforming it into reciprocal space. I can just define a number, A of Q, which is the Fourier transform. Then my whole expression, and the scale of it, the physics, this is the Thomson scattering length, just the number. Here's my spherical wave going out, and that's modified by the Fourier transform of the charge density. Now let's go to what am I actually going to measure? This is electromagnetic radiation. I don't actually measure the electric field, I measure intensities. Okay, so I have a detector, whether it's film, a photodiode, a CCD detector, a pixel array detector, it doesn't matter how I detect it. I detect intensities. Okay, and the signal is the number of photons per second crossing into the detector, which has a given size. Right, so it's the energy per second flowing through the illuminated area on the sample, that's A, this is the size of my, divided by the energy of each photon, which is h bar omega. So if I assume that my incident beam has some intensity I0 and a cross-sectional A0, that my detector has some area of my detector, which it's convenient to write it as the square of the distance from the sample times the solid angle. We get this relationship here. So this is the scattered intensity divided by the incident intensity. A is the radiated field squared divided by the incident field squared. And this is the area of the detector, and this is the area of the beam. A very simple relationship so far. Let me plug back in my previous numbers. And it's actually also used to, I want to normalize the scattered intensity by the incident flux and by the solid angle of my detector, which is this thing here. So I just calculate this, plug everything in, it goes into here, or I plug these together, or now you see why I wanted to write the area as r squared times omega, because it cancels out an r squared from here. So the distances go away. All these absolute value signs take care of these complex valued things. Basically, everything falls away except the square of the Thomson scattering cross section and my Fourier transform of the density. So in the end, my differential, my scattering cross section is a fundamental constant times the Fourier transform of the charge density. And so when we measure this differential scattering cross section in a scattering experiment, we are directly probing the electronic density of the sample. And so this is the first key result. And in the end, after all that algebra, it's a relatively simple expression here. That the scattering cross section is the square or the Fourier transform of the charge density. Okay, I think maybe I should pause here for a second and see if people have questions. Although, let's see, I can't see any of you at the moment. How can I restart there? Are there, does anybody have any questions at the moment? I guess I should ask Lamari, are you still hearing me?
Yes, yes, we are here, and there's no questions and no questions in the chat. So I guess you can go on.
And then I'll go forward.
I think you should also recommend a book to help us. Maybe.
Yeah, absolutely, Sandra. Good point. I will post my copy of my lecture notes. All of these slides I'll post online, and I can give you some references to several standard textbooks. I'll put those in an email after the lecture.
Perfect. Thank you very much.
Okay, so let's step forward. So I guess if you have a question, since I can't see you, unmute your microphone and yell at me, and I'll stop and answer the question.
If you write in the chat, I'm watching the chat, so
Okay.
you can write there too.
Okay, great. So just stop me if I'm going too fast or too slow or whatever. Okay. Okay. So let's do a special case then. And I talked in general about a charge density, but the world around us is actually made up of atoms. We don't just have continuous distribution of charge hanging around most cases. So let's an important special case is a single atom. So if we think about what that would look like that there would be an atomic charge density of an atom. Let me call it rho sub A. Okay, and then to get back to my previous calculation, I want to calculate this Fourier transform. I'm just going to define that to be a f of q because we're starting. This is the initial point. I'm going to put a 0 up here just as it's sort of the smallest thing. So then we can look at, just with this formula, I can do a couple of really quick ideas. Let's get a handle on what does this thing look like and what does it mean? And first, let's look at the limit where the scattering vector q is 0. This formula then simplifies very much. So if this is a 0, this exponential becomes a 1. Now I just have an integral of the charge density over all space. And for an atom, that's just its atomic number. All right. So if I look at F0, when Q is equal to 0, that's just the atomic number. All right, so then, so if everything is in phase, Q is equal to 0, the whole signal just scales like the number of electrons in my atom. If I go to the opposite limit, I let Q go to infinity, I get in the case where then very small changes in R cause us to oscillate back and forth, and I get as many pluses as minuses, and everything is wiped out. So at the limit of Q going to infinity, this is 0. So what I expect then for this function f to be a smooth function, the same way the atom in real space is smooth, but when the intercept at Q equals 0 should be Z, the total number of electrons in my atom, and then as I move out to infinity, that will go to 0. So that this in Q space as well as in real space, this charge density is localized around a single point. Okay. Now there's another, we need to make some minor corrections right now. And as we know, atoms are not just, they're complicated objects. And the electrons in an atom aren't free to do whatever they want. They're actually bound in definite orbits around the nucleus. So, and indeed, this is where all of chemistry comes from, right? That there are specific energy levels, binding energies, and so on. And so that's just the real world. And so this has impacts then on the kinds of interactions which are possible. So for example, if you think of a valence electron in any atom, if I come in with a photon whose energy is less than the binding energy of that electron, it cannot be absorbed. Because the minimum amount of energy you can do is to take an electron and knock it out. So take your highest, whatever your valence electron are, the least bound electrons. And so if the smallest amount of energy which can come at a given frequency, which is defining my beam, is a single photon. And if the energy of that photon is not enough to unbind an electron, they can't be absorbed. Okay. If I come in with higher energy X-rays, of course, they can be ejected, absorbed and ejected. Also, electrons that are more loosely bound can be shaken differently than the strongly bound electrons. And so the more loosely bound states respond more like free electrons. But just sort of qualitatively expect the ones which are really rigidly bound not to vibrate as much. And so that they won't radiate quite as much. And so we're just going to make up some numbers here, that F prime will be the amount by which, it's going to be less than 0, but it's sort of the amount by which the binding keeps that charge from shaking. And then if there's some absorption, we'll have an imaginary part as well. And let's move forward. So with that caveat, then, I can now create a molecule by just adding up atoms which are at different positions. So now, the Fourier transform of the charge density of my molecule is just the sum of the Fourier transforms of my atoms with the appropriate phase factor. All right. So I've now gone from a single charge, point charge, to a continuous charge, to an atom, to a molecule. And so this is now the molecular form factor. And I still have to sum. The sum now is the J's are the positions of the atoms. Okay. Then I can go to a crystal or a big solid. Starting with the crystal, the idea here is a collection of atoms of various types. So I could do salt would be sodium chloride, so you could have two kinds of atoms, and that the atoms sit at various positions. But now I have a truly awesome number of atoms. We're talking about numbers that are large, perhaps compared to 10 to the 20. So we are never going to be able to do an exact solution of this without making some assumptions. And so the basic idea for a crystal is that the structure is a periodic lattice, and that there's some kind of a unit cell which is repeated over and over again. So if I use capital R as the location of the nth unit cell, and then I can use tau sub j as the position of the jth atom in the unit cell. So it's convenient to think for a moment just to use the unit cell as a molecule. So their molecular form factor. So where are all my molecules? Then this whole thing for the Fourier transform of the crystal, here's the Fourier transform of my atom. I put the phase factor in to get the Fourier transform of either my unit cell or my molecule, the same kind of idea. And then I have additional phase factors as I replicate this thing over and over again. And I get
Joel, we're really losing your audio.
Okay,
Okay, now we're back.
am I back? Okay.
Yeah.
So I see I'm having both video trouble and power trouble. This is a great day here. Okay, right. So, so far we've been talking about scattering. In my classical picture, the scattered wave or the radiated wave has exactly the same frequency as the incident or driving wave. Okay? And in that sense, classical scattering is absolutely elastic scattering. Okay? Now, we already mentioned about absorption and so on. And so in a quantum mechanical situation, that doesn't have to be true. That an X-ray can lose energy to the scattering object. And there's a couple of ways it can happen. The simplest one for a free electron would be that the X-ray just gives a little bit of energy to a point charge. And this inelastic scattering is called Compton scattering. And this is what else can I turn off? Try and reduce my battery here. I'm just going to close a bunch of stuff and see if that helps. Okay, maybe this will help my battery. Okay, in this classical picture, any battery left at all? Yeah. Okay, not Compton scattering. This is the simplest picture of Compton scattering. I have a wave, an electromagnetic wave coming in from the left. It runs into a point charge, which is at rest. After it collides, it gives a little bit of energy to the point charge, which starts to move and goes in a particular direction. And then there's another electromagnetic wave which goes off in a different direction. And so in this kind of a picture,
We're losing you again, Joel.
Okay. Let me turn off my video for the moment then. Can you see me and hear me now, Lamari?
Yes, I can hear you now.
Okay. Maybe not using my video will keep me. Okay. But we'll just go with the PowerPoint. Did I just lose you?
Yes, we can see and hear you.
Okay. Okay. So in the Compton scattering, there's a wave coming in with some well-defined momentum given by its K value. After the scattering event, we have a new one, and we have a moving electron. If I just assume that conservation of energy and the conservation of momentum, I can completely solve this equation. And I don't want to do it for you, but the answer is given here in terms of the ratio of either K vectors or wavelengths or energies. And it's completely determined that if I know what angle the photon went off at, I can calculate exactly what K prime is. Or if I know K prime, I know where it went. There's no degrees of freedom left, is one thing. So the change in the wavelength of the photon is just proportional to this new number, lambda c, which is the Compton scattering length. And again, it's just a combination of fundamental constants. It's Planck's constants, the mass of the electron, and the speed of light. Right? And it's also a tiny number. So there are two fundamental lengths which describe light, X-rays in particular. We have the Thomson scattering length R0 and the Compton scattering length lambda c. And if I look at the ratio of these two, that's the fine structure constant. This is this unitless number, a very famous number, but it's basically the ratio of the strength of scattering to elastic scattering to inelastic scattering is the way to think of it. So there's what this tells you, though, if you look at it, is that absorption is much stronger than scattering. In some fundamental sense here. But there's some things which save us here from a structural point of view. And the first is that Compton scattering is incoherent. What this means is that the simplest way to think about it is because the frequency of the Compton scattered photon is different from the frequency of an elastic scattered photon or of the incident wave, they cannot interfere constructively. So they basically now don't see each other anymore and propagate independently. Also, the Compton scattering cross-section varies very slowly with scattering angle. And that previous formula, it just kind of goes from 0 to 1. You can't do much about it. But it does give us an easy way to subtract it. Then we know exactly what it's going to look like in any given experiment. The particular example I showed assumed that the point charge was initially at rest. If the point charge is not at rest but has some finite momentum, we can jump to a new reference frame and using special relativity, do the same calculation in the rest frame of the particle, and then jump back to the lab frame. And so there's a couple transformations, but it's all we have to know is what is the initial momentum of the point charge. And then so we can do all of these calculations. And in that sense, Compton scattering can be used to measure the electronic momentum of distribution. So if I want to know the momentum distribution of an atom, I can do that through Compton scattering. Okay, photoelectric absorption. This is the other thing that we're all familiar with, is that sunlight feels warm, X-rays, chest X-ray, we look at the absorption and so on. So where is this coming from? And it's all photoelectric absorption. And the simplest idea is shown here, on the right-hand side is the energy level diagram of an arbitrary atom, where we have the lowest lying, this might be the 1s level, 2s, 2p, and so on. And so what happens is in the case of an X-ray, comes in and it has enough energy to actually excite an electron all the way out, or perhaps to a higher energy level up here, some other bound state below the free electrons. And so this kind of absorption requires an atom. So the true absorption, or the taking out energy out of the electromagnetic field, you can either do Compton scattering, where the electron gets a little kinetic energy in the continuum, or if it's a bound electron, you can have an absorption event. And the absorption, though, requires an atom, this photoelectric absorption. And you have to either put the atom into an excited state or into an ionized state. Okay, so quantitatively, we describe absorption by the linear absorption coefficient. And all that tells me is how many photons are absorbed in an infinitesimally thick slice dz. And the basic idea is I say, well, it should be proportional to the thickness of my slice. The number that I absorb should be proportional to the number of photons I have. And I'm going to make up a number mu, which is the proportionality constant. But as soon as I do this simple thought argument, I can immediately integrate this expression, and I come up with and I see this exponential decay of the intensity. Whatever it was at the beginning here, it decays exponentially with this factor mu here determining the length. So if I want to compare that to the number of absorption events, and I have to do a similar thing where I have a thickness, I need to know the number of atoms, I need to know the cross-sectional area of basically of every atom in here. So this is just the number, so this is photons per area, and so here's an area coming through here. This is telling me how many, this is the effective volume of an atom, and this is the density. Multiplying these things together have to be the same number. So I can compare my absorption coefficient to the cross-section for absorption through this very simple formula here. It depends on the absorption coefficient, depends on the number of atoms per unit volume times the cross-sectional area. And then if you go back and say, okay, what's the, I'm changing from to mass, back and forth from number to mass, I have to go through Avogadro's number and the atomic number and so on. So I can write it in different ways so that these were per atom. Now we're getting more towards chemistry here, where this is the mass density and the atomic mass number here. So just same equation, just different points of view, how to calculate. Okay, and then we get to the standard things that we're familiar with, where we can now calculate very simply that away from all the absorption edges, the absorption should then go like a frequency cubed or a wavelength cubed, except when I cross over an energy, then some more elements can contribute, and I get more and more absorption as I go higher and higher levels. But the photoelectric absorption then goes approximately z to the fourth, then have all of these jumps here. And so depending on where I'm working, I'm more or less sensitive to the absorption. But then the net effect then is that I begin to see different elements absorb different radiations at different levels. And I can start doing absorption images which are sensitive to atomic number. So X-rays are really unique in the sense that they were discovered by Röntgen, and within a year, medical doctors were already using them to diagnose illness. Now, unfortunately, there was a lot of people were damaged by that. They didn't realize how harmful X-rays could be. And then people got radiation sickness. But it's one of the first cases where scientific discovery went directly into medical practice very soon. Many of you have seen the pictures of Röntgen's wife hand wearing a ring. Quickly, people realized you could see broken bones, various. It's not as good at soft tissue, but or if you had were injured in battle and had a bullet or something, they could actually see where it was. This was one of the very early successes of a scientific discovery going right into medical health. Okay, let's see. Can you still hear me? I'm getting error messages that my audio may not be coming through well. Am I still audible?
Yes, we can hear you.
Okay. Okay, refraction and reflection. And so far, I've been talking exclusively at the atomic level, but since X-rays are electromagnetic waves, we also expect them to do the kinds of things you associate with visible light, right? Where I can have refraction effects, which brings in the lenses in my glasses. As reflection, there are mirrors and things. Both of these you expect to happen. If you go back through your university physics textbooks, you'll see that all these things are related to the index of refraction in visible light. Right? And for X-rays, it turns out it's convenient to express the index of refraction, N, as 1 minus delta plus I beta. And the reason this is useful is what you see is the real part of this correction, delta. For most materials, it's on the order of 10 to the minus 5. So the index of refraction is very close to 1, just a tiny little bit different. And solids in air, that number is 10 to the minus 8. And the imaginary component in most cases is smaller than delta. So most cases we can ignore it. And that will be the absorption part. Now the key thing to notice about this expression though is that for X-rays, the index of refraction is smaller than 1. That means that the phase velocity of X-rays in materials is greater than the speed of light in vacuum. So this doesn't violate special relativity because information travels at the group velocity, But it is true that the phase velocity is going faster than the speed of light. Right? And then we end up with the standard kind of things that you associate with visible light, right? Where the cosine of the incident angle is n times the cosine of the transmitted angle. So here I've made the approximation that in air that n is equal to 1, so you don't see it. Also, you may say, hey, wait a minute, Snell's law is sine theta, not cosine theta. Joel, what are you doing? And that's a convention. And that in optics and visible light, people usually measure the angle of incidence from the normal to the surface. In X-rays, because we're used to doing diffraction experiments in Bragg's law, we measure it from the surface. So there's just that if I had measured by the angle up here to the normal, these would be all sines instead of cosines. Same exact expressions, it's just we've chosen to measure it with this small angle here rather than the big angle here. Okay. So the difference for visible light, though, is that the index of refraction is bigger than 1. So in glass, the index of refraction is 2 or 3. And you get the normal things you're used to, where you come in at a small angle and you leave at a larger angle and you come through. For X-rays, it's the opposite. I come in with a large angle and come out at a shallower angle. And of course, then you get into these interesting cases where in visible light, we call it total internal reflection, where if I come in small enough, I can't even go through here. And for X-rays, the optically dense part is vacuum, and so I can get total external reflection. And so this is the origin of how all of our X-ray mirrors work, why we have to come in at glancing angles. If you go back to the algebra, you'll find out that this critical angle for total external reflection is given by that number delta. And so it's basically the square root of delta. And that's why our X-ray mirrors, we tend to use very high electron density materials, platinum, for example, or rhodium, very high Z atoms that we can pack closely together to get this up as big as possible. And at typical values for this critical angle with a platinum mirror at 10 kilovolts are about 1/4 of a degree. So we can, there's a little bit of room to work here, but not much. But that's how we can make a real X-ray mirror. Okay, now in the modern world, we're getting all kinds of new kinds of sources, and people worry about what they call coherence. And this is going back to my earlier statements about the wave packets. So real beams of X-rays are not just ideal plane waves, which go on forever and ever. They have a finite size and time, and because they have a finite size and time, they have a finite spread in frequency, and so on. If they have a spread in frequency, they have a spread in wavelength. Okay? So, so this leads to two kinds of differences from an ideal plane wave. First, they're not perfectly monochromatic, and two, they don't propagate in perfectly well-defined directions. And so let me do the frequency one first. And I can come up with a description for, I describe the how non-monochromatic it is by the length scale over which it dephases. So if I look at, here's my original wave going at lambda, these are lines of constant phase. If I compare that, if there's some spread, delta lambda, and I look at lambda minus delta lambda, it will repeat here. And at some point, an integer number of lambda times delta lambda will equal one fewer wavelengths of lambda. Yeah. And so, so I'm going to set n times lambda equal to n plus 1 times lambda minus lambda by 1. And then I can define basically this length here to be twice my longitudinal length. There's a 2 here for convenience later on. But the basic answer, just dropping out, plugging this into here, is that this longitudinal coherence length is given by lambda squared over delta lambda. So the smaller delta lambda is, the longer I have to go. And I get my longitudinal coherence is a measure of how monochromatic my beam is. Similarly, there's a similar thing in angle. Oh, and this is, before we talked about, it was delta t times delta omega is 1. Here it's delta x times delta theta is 1. Same kind of argument, but so I have to come up with this basically the size of my source, or make a very similar argument of, how far can I go sideways before, or I can't tell which phase front I'm on, and you come up with a transverse coherence length, which is given by the distance from the source divided by the size of the source times the wavelength. And these then are definitions of the longitudinal and transverse coherence length, which all the synchrotron people love to talk about. So what it does have an impact on us is it places a limit on how far apart two objects can be and still produce interference challenges. So the more coherent my beam is, as the volume which actually participates in diffraction grows and grows. So a more coherent beam means that now this can be good and bad. What it means is my diffraction signal may now encompass my whole sample, but my sample may have many independent domains. So you may like this or you may not like this, but it basically tells all of our calculations have been over the coherent part of the beam so far. So when you think about coherence, you should, in your back of your mind, you should think that's the volume in my sample. If I take the transverse length times the longitudinal length, that sets up a volume. That's what's participating in a scattering or diffraction event. Okay, so how do we make our X-rays? Okay, so a really quick history of X-rays here, and I mentioned that in 1895, Röntgen discovered X-rays. Basically, he was doing experiments with voltages and so on, and nobody knew anything about what was going on, and this was a true discovery. Nobody thought they were coming out, and that's why they called them X-rays. X meant they didn't know what it was. About 15 or 20 years later, Phonomenology discovered diffraction and began to explain it. Within a year, the two Braggs, this is a father and son team, they invented crystallography. Phonomenology also had major contributions in diffraction, but the two Braggs got crystallography first. And that at almost the same time, Coolidge invented the X-ray tube. And this is basically all of the conventional X-ray sources in the world are still based on rough and disk design. And this is an example of it, and the idea is very simple. You have a filament here, you run a current through it, it boils off electrons, like any other light bulb. You put a potential from your cathode to your anode, the electrons come whacking into the material. That excites the atoms, and then in an inverse absorption event, as an electron decays back down to the ground state, you emit a photon, and these are the X-rays. Okay, so then this all has to happen in vacuum, and you need cooling water and so on, and this object is called the Coolidge tube or hot cathode tube. You need to have reasonable vacuum and so on, and the limitation is there's tremendous amount of heating. If this electron beam hits this metal piece, and so water cooling is the limit thing. How can you keep from melting this thing? You think of this like an electron beam arc welder coming in, and eventually you're going to melt your anode. Not too much later, the rotating anode was invented, and it's just a heat management idea. So the basic idea, this thing here is a disk. You're seeing it from the side, and so it's spinning around this axis as it's still water cooled. And the basic idea is that the electrons hit it, the X-rays come out. But as it spins, it just moves that electron beam off at the hot spot on it. So it's going around and around, and so that you get a much bigger heat area, but while still having a small illuminated area to create the X-rays. It's, and the true tragedy of all this is that the tubes are so inefficient. Right about 1% of the electron beam energy is actually converted into X-rays, which go into 4 pi, and then we just get a little tiny bit of solid angle coming out of here. So first, most of the energy doesn't go into X-rays, and then we can only look at a small part of it. Nevertheless, this is how your dentist office works, rotating anodes work, and so on. So almost all medical devices are this way. Until more recently, we've replaced anodes maybe with liquid jets of metal and so on. But the whole problem is heat load. It's not a fundamental problem. It's just heat. It's so inefficient. The anode has a couple of other challenges. Is that a lot of the radiation coming out is not the characteristic radiation you want. And it's because there's not just electrons in your atom, there's also a nucleus. And so as the electron comes flying through the atom, it can elastically scatter off the nucleus, and that gives me the Brunstrom. It can elastically scatter off the nucleus, and that gives me larger angle deflections, and so on. Or it can excite electrons inelastically, which then decay to a characteristic spectrum. The characteristic spectrum is given by the atomic, so this is, say, the 2p to 1s transition here, create the well-defined. So if I come in with my high energy electron beam and knock out a core electron from here, the atom can decay, emitting its characteristic radiation. So if I combine all that stuff together, my emission from a rotating anode or a tube looks something like this. This is, for example, from molybdenum. But at short wavelengths, I have the characteristic emission K alpha and K beta, the 2 emission lines coming up. These are well-defined energies, but my Brunstrom continuous radiation forms a big swath through here. So I get a very bright narrow line on top of a background here. But the highest energy I can make here is completely determined by the energy of the incident electron beam. Until recently, this was the only way we knew how to make X-rays. But going back to our original discussion, radiation is developed by accelerating charges. And so whenever you have a circular accelerator, you're going to be accelerating charges in that centripetal centripetal acceleration to counteract the centrifugal force. And so the radiation gets its name from a very specific type of particle accelerator, where it was first observed. However, it's now used as a generic term for the radiation from charged particles moving, being accelerated. So in a modern realization, there's 2 sources of synchrotron radiation at a facility like CHESS. One is the bending magnets, which just keep the particles going in a circular path, and the second is insertion devices, such as wigglers or undulators. In practice now, almost all of the beamlines in the world are fed by undulators, although wigglers still play an important part, and many facilities actually still have the bending magnet beamlines as well. But here's an old picture of the old Caesar before the upgrade, and it just the lab just briefly. There's a linear accelerator which accelerated electrons and positrons to about 100 MeV. It went into a synchrotron, which boosted from 100 MeV to about 5 or 6 GeV, was transferred into the storage ring and went around forever at this point. If you look in the tunnel, here's a picture of the old tunnel. On the inside diameter is the synchrotron, and on the outside diameter is the storage ring. We used to run both electrons and positrons, and so radiation would come out into 2 chess areas, and that there was a particle physics experiment in the middle. What Chess U did is we took out the detector, and we only run particles one way now, so I have a much bigger floor down here, and we're able to optimize the optics. So how do you compare all these machines? And introduce a new concept. It's called the brightness, and formally it's actually called the spectral brightness. But the idea is I want to get many things into one number. And the first thing is the intensity is just the number, or the flux is the number of photons per second in the beam. And this frequently is what you care about. But there's a couple things we also have to know. We need to know how well collimated is that beam. And so it's an angular collimation. Is it completely parallel, or is there some divergence? I need to also know what is the area of the source. If I have something, if the bigger the source is, that actually affects my calculations as well. And I need to know what is the spectral distribution or bandwidth, delta E over E of that beam. And so if I take all of these things, I really want the number of photons per second, but I care over how many milliradians was that coming out, over how big an area of source, and how much energy bandwidth was that. And we call that the spectral brightness. It's the same number that if you look in an optics textbook that people use for visible light. So then how does synchrotron work? Well, if we just start really quickly with the bending magnet, as the electrons go whipping around, they're being accelerated. They radiate their dipole pattern that we were just talking about earlier in the lecture. The only difference is now they're going at the speed of light, and so instead of that circular distribution pattern, it gets folded forward. And it gets folded forward into a radiation cone. The opening angle is 1 over gamma, where gamma is the energy of the electron divided by its rest energy. So it's just a normalized energy. So the rest energy of an electron is about half a GeV. So when we were running 5 GeV divided by half a GeV, and you get 10 to the minus 4, is the opening angle. So that's about 1/10 of a milliradian, which is about half a degree. Okay, so all of that radiation, which used to be going out into a sphere, is now being folded forward into a natural opening angle. And this is one of the key things about a synchrotron. You have a naturally collimated X-ray beam comes off of the source. We can, very simple arguments, we can calculate what is the spectrum of the synchrotron radiation. And you need to know things like what is the magnetic field of your magnets. That's the Lorentz forces. This is just E times V cross V. The centripetal acceleration is V squared over R. Newton's second law. You put all this stuff together, you get the momentum is the radius of your storage ring times the charge times the field. So this is still valid for the relativistic case, so we need to slip a gamma in here. And in the super relativistic case, where it's actually moving at the speed of light, we can replace V by C. And if you just drop all of these things together, you come up with a very simple formula relating the energy of the storage ring, the mass of the electron, the radius of the storage ring, the charge of the electron, and the available magnetic field in your bending magnets. And these things are all, the reason chess is so big is because we want to go to high energies, but our magnets can only get to a certain size. This is why high energy particle accelerators are so large. We can get to the spectrum just by really simple arguments. That's where if I know how long it takes my electron to go all the way around, I can define a time t for how long does it take that electron to traverse that opening angle. And if we go back here, this opening angle is 1 over gamma. So I can just ask, delta t is how long, the period of revolution, the frequency, and so on. So I can calculate this delta t. Got to be a little careful in jumping to, this was calculated in the rest frame of the electron, so I got to jump to some special relativity here. But basically, the inverse of delta t gives me the frequency width. So the inverse of the pulse width gives me the frequency spread, which goes from 0 up to a high energy. So this is the critical energy of mine. And you can through here. And all of these are completely determined by these other energies we had before. So that's the bending magnet spectrum, and I see something like this. That's where there's a critical energy, and I can, so this is the spectrum, just from the simple argument I just gave you. We calculate the spectrum of the emitted light from a bend magnet of a particular, don't worry about the formulas, but everything is just in there. But we're greedy. I don't, I want more. And so the first thing we can do is to say, well, why am I limiting myself to just one bend magnet? I could add up a whole bunch of them. And if, if I go left and right and then left and then right, they will add up on top of each other. And I should get my, the number of poles times my field. And indeed, that's what a wiggler does. So if you look at it from the top, it wiggles the beam back and forth. And then you get this radiation pattern coming out. And this angle here, it's convenient to write it in a normalized number in units of gamma, which was the opening angle. Because if you look at it from the side, the vertical angle is still 1 over gamma. And so that depending on the strength of my kicks here, my wiggler, this angle is just k times 1 over gamma. So k is a really useful number for us to use. So if we can write down what it is here, but something interesting happens. If I go back, if k is less than 1, my beam never gets outside of itself. So it can interfere with itself. And so k equals 1 is kind of a dividing line, where if k is large, a radiation of different portions of the trajectory add up incoherently. If k is less than 1, they can add up coherently. And that's what we call an undulator. And the advantage of the undulator now is, it doesn't wiggle very much. And so I get this open angle here, and now everything's adding coherently, very much like in a phased array radar or something. And so this number gets even smaller. It goes like the square root of the number of poles. So my opening angle gets smaller and smaller in both directions. And now I really get a lot of it. So it's a little counterintuitive here. But what we've actually done is by lowering the magnetic field from a high field device to a low field device, we actually focus the radiation in an interference effect onto the central cone. So although the total radiation produced by my undulator is less, the peak radiation is much higher, than because of constructive interference. And so I get a sharper peak, so I can be sharper in angle, I'm going to be sharper in energy, and I'm going to be, so for most of our applications, this is exactly what you want. And so Chess has a long history of insertion devices. That when I first got here, Chess was like the world leader in wiggler technology. And Ken Finkelstein was one of our original wiggler designers. And Chess did some of the very first tests for undulators, for undulator A, which has been the workhorse for the advanced photon source, was tested here. And these days, still lead in undulator technology. Here's a picture of Sasha Temnek, who's sort of the wizard at Cornell for developing insertion devices and so on. And this idea of the Cornell compact undulator, it's a permanent magnet device, and has it's small, light, and powerful. And so the details here aren't important, but we continue to optimize these kind of devices going forward. And so all of almost all of the ChessU beamlines work on these Cornell compact undulators. The exception is Sector 1, which runs off of one of the wigglers that Ken Finkelstein built several years ago. So the spectral brightness that we're talking about was inversely proportional to the source size and the divergence. And that source size and divergence are things which are properties of the electron beam. And it's known as the product of the source size and divergence known as emittance. And so the way we actually get the properties of the X-ray beam is we have to start, we can calculate the emittance of a photon beam from a single electron. If I just ran one electron through, it will have an emittance which is completely determined by fundamental physics. Okay, and that's the best you can possibly do. If I then run it through the storage room where I have many electrons, then I have to calculate the admittance of the electron beam in the storage ring. And then for every path of an electron through the storage ring, I have to add up the emitted photon beam. And that's a convolution. And so the minimum admittance of the photon beam is if the electron beam does not contribute. So that I can calculate that from the uncertainty principle. So what is the diffraction limit of a photon? I can start with my, this was the undulator equation from before, and I also know for the angle opening from my coherence calculations was lambda over L. I can put all these things together in various things here, and I come up with, this is the angular opening, similar argument, this gives me the size, multiply them together, and I get this is the fundamental limit on the size, this is the fundamental limit on the angle. What you see is when I multiply them together, I'm going to get lambda over 4 pi. That the L's will cancel out, and so on. And so that's my fundamental admittance. Now this is going to be a little tricky for many people, going really fast here. But what I'm plotting here, there is this source size on one axis, and then here is a position on the storage ring. And on another axis is the rate of change of Z or the rate of change of sigma. Okay, and so this is a phase space plot for the source size, angular divergence. And if I move down the storage ring, what will happen is I can trade off some angle for some position, and the ellipse rotates. It goes around and around. So the ellipse can be rotated by as I go through each bending magnet through my magnetic field. The photon beam admittance has to be convolved with that electron beam admittance. And so if this is my photon, it goes around and around, and then I have my electron beam admittance here. The effective, so this is of a single electron, this is my convolution electron, and my phase space for both is out here in the green. Okay. And so what I find is that because of my storage ring, there's a fundamental limit to how good I can make my, I can never make my electron beam, my photon beam better than my electron beam. And there's a huge challenge here for getting to the ultimate limits, and that's that, storage rings are storage rings. And the basic idea is the electron goes around, it radiates a photon, which means that it lost a little bit of energy. When it loses some energy, it has to shift its orbit, which means it slows down a little bit, it changes its radius, and it goes through an RF cavity, gets a little kick, and it restores the energy, and the orbit shifts again. And so I get a steady state equilibrium distribution. And it takes about 10,000 turns going around the storage ring for this to take into place. So each bunch of electrons can have a million electrons in them, and they're all moving around. And it's really an equilibrium thing. Think of it like an ideal gas or something like that. So to minimize the admittance of my photon beam, I have to minimize the admittance of the electron beam. Okay? And so this sort of equilibrium nature of the storage ring places the fundamental limit. I can get beyond this by going from a storage ring to a linear accelerator, a LINAC. And this was, you may have heard that originally Cornell had an energy recovery LINAC idea. The basic idea is if I have an electron beam, I can accelerate it in a linear accelerator, or I don't have any of these equilibrium considerations. If I then run that nice electron beam through an undulator, I can have a really beautiful X-ray beam. And the problem is if I want 100 milliamps at 5 GeV, that's 500 megawatts, it's just too big a power load to be reasonable. The idea of the energy recovery LINAC is a linear accelerator is also a linear deaccelerator. So I could ramp up the electron beam, get my X-rays off, bring the electron beam back, decelerate it through the cavity, get my energy back, and then use that energy to excite the next electron bunch. And Cornell, 15 years ago, had a big project for the Energy Recovery LINAC project, which here's the Wilson Labs. It was going to be a massive thing going way out to the college and back. Now, that did not, although it looks nice on paper, the funding reasons is not possible. More recently, we have a program known as C-Data, the Cornell Brookhaven Energy Recovery LINAC Test Accelerator. This exists in the room right next to the chest experimental floor, where we inject electrons. They go through a LINAC, goes around the ring, and then can be deaccelerated into a dump. This particular one actually goes around 4 times up and 4 times down. So the next time you're at chest, you take a look at that over there. You can actually, so that the very beautiful demonstration experiment on the linear. Let me skip that part. The next example many of you have heard about are the X-ray free electron lasers. And this is very similar to the concept I was just talking about, with the exception that if my electron beam is small, or the bunch of electrons is actually small compared to the wavelength of the X-ray, then they will all be accelerated in phase and begin to act very much like a single superelectron. This is very similar to the idea of the form factor at Q = 0, where everybody's in phase. So if I can get small enough bunches, I can do this. It turns out that there's a higher order interaction between the electron beam and the radiation field, which tends to bunch them together automatically. You use this instability to bunch the electron beam, and that's known as the X-ray free electron laser. And so you basically start with a long LINAC, you accelerate the electron beam, you take it through a very long set of undulators, which starts to radiate, right? And that radiation then bunches the electron beam. And then the very last part, the LINAC, those little micro bunches radiate as superelectrons. And so it sounds difficult, but it works. And there's several examples in the world right now. The LCLS is running at SLAC. The SACWA is running out in Japan at Spring 8. The European XFEL turned on a couple of years ago, and Flash is also there, lower energy. And these are working in Hamburg at KZ. There's the Korean XFEL and the Swiss XFEL, and there are more around the world. So you see these are coming on in different places. Okay, and I think I am not just running out of battery, but time. And so the lecture tomorrow will talk about scattering by condensed matter. But I think I should stop and take questions and answers and make sure that there are people still there.
Okay, thank you, Joel. If there's any questions, we still have time today for that. I think most of us will have to read a little, so
let me
and go back to the presentation so
yeah,
we can.
Yeah. Let me upload the slides and put some textbook references and things for people. Oh, and then maybe tomorrow I should start by answering lots of questions.
That would be great. I think so.
Okay, so that people should, or I can re-aim the talks if it's if this isn't the appropriate level, let me know and we can go back and do it again.
Okay, I'll send some emails and ask questions to people if they don't feel comfortable to talk to us here. So I'll let you know if we need to go back.
Yeah, I would like people to feel comfortable asking questions, so encourage them to. That's how we learn. Yes,
of course, I'll do that. Well, if there's any question, if not, you're going to receive either through my email or Megan's email the information you need to connect to the presentation, so you can ask more questions tomorrow.
Thank you, Professor Brock.
It's Professor Miller. Nice to see you there.
I learn something every time I hear these talks. Eventually, I'm going to figure out how chess works, and really be in trouble. Well, that's actually the cool part about chess is that, I mean, you don't totally know what we do, right? It's like that there's this interdisciplinary thing that happens between, you know, when like what we do is with metals and using diffraction. We don't have to know all these details. We just have to trust what you guys do and those effects. But I think that's really one of the things that that students can sort of take away is that you sort of, what grad school does is you pick the area that you want to make your field. And the really exceptionally cool thing about like an academic career is you can change that. You know, you can change that. And I like for instance, I kind of forgot all about diffraction until you know, the early 2000s. Now and then started thinking about how we use them to, you know, interrogate, you know, structural materials. So it's great. It's a really cool place. Dig in.